Welcome.
Thank you. Hi, everyone. I'm Parul, and this is my first time speaking at Nbpy Python. Uh, uh, I will be talking on Python scientific sorcery with efficient code. Uh, I'm going to talk about some of the tidbits around open source Python scientific library that people would be using already, and I want to make them write efficient code. If you're an ML engineer, you might already know most of it, but if you don't, and if you're just a beginner, then this is the place to go. We will learn some of the basics, the underlying principles on some of the popular open source libraries, such as NumPy, Pandas, polars, that are basically used in the scientific computations. I hope you like it and end up learning something new today. But first of all, who am I? I'm an engineer at Meta. I work for Python Foundation team, where my focus area is mostly around the third-party packages, and to ensure that the outside packages work well with the Meta ecosystem. Now, this talk has nothing to do with that. That work basically exposed me to some of these libraries, which I find interesting, and I started playing with them in my free time. So, the ML pipeline. Before going deeper into the basics, I want to talk about what a general ML pipeline is. Oftentimes you may hear other words for this. You may hear something like AI lifecycle, data cycle, AI pipelines. In my opinion, it's all the same. So this is a very oversimplified way of what a pipeline looks like, where you have data processing. Data processing is where you collect data and you ingest it from various sources. You clean the data, you pre-process it. Pre-processing could be handling the missing values, or leaving out the outliers, or doing any type of data normalization. You then reform it, and you basically extract the relevant features that will be input into the next stage, which is model training. Model training is essentially you select an ML model that your scientists would be using or would be creating, and then you train your data on it. Then comes model evaluation. It's basically the time when you've trained your model and you want to evaluate how it performs on a different data set. You normally compare the model's performance with the past iterations of the same model or a different model in terms of accuracy or different scoring mechanisms like precision, recall, F1 score, etc. Then comes deployment. Once your model is good to go, then you want to deploy it out. You want to ship it out to your services and make actual use of it. This is where deployment comes into place. You'll hear things like scalability, reliability, security, compatibility with the infrastructure that's already there. All of this is deployment. And finally comes monitoring and analysis. Over here, you want to constantly monitor how well your model is doing with the real data that it's getting. And from there, you want to have some sort of feedback loop or some sort of mechanism, some analysis that will help you refine the model in future, and the iteration goes on and on and on. So I'm going to go through some of these spots, which I feel like we can have more efficient code than what I've generally seen people do. So in terms of data processing, we can go from here. Data processing, there's a lot of debate in terms of what is better. Is it data or the model? People have different opinions about it. I'm just going to leave you to whatever you feel or you think is better. But basically, we want to make data processing faster and make our lives easier with that. People use Spark. Spark is the industry standard framework for data processing. It is basically designed to process big data and analyze them. It's widely used for its speed in comparison to the traditional Hadoop MapReduce, wherein most of the operations are done in memory, and so they're faster. It's also used for ease of use. In general, it has a very high-level APIs in multiple languages, such as Scala, Java, Python, R, so it caters to a wider set of developers. It also has advanced analytics in terms of it has built-in modules for different things like SQL queries, streaming data processes, graph computations, and so on. And finally, it's scalable. You can run a Spark on a simple machine like this one, or you can have it on thousands of clusters altogether for parallel computations and whatnot. Here's an example of how you'll store and read from Spark. I'm going to go into the details of it soon, but over here, the thing to know is that I'm using a traditional CSV file. You can even use a text file. It depends on what you're using. But the point over here is that the CSV files can end up making your code really slow. The reason for that is that all the aggregations that happen can be slow because CSV is row-wise setup. So what do? People introduced Apache Spark to it. As opposed to how the CSV files are, Apache's Parquet files are basically designed for aggregations, for data computations. They're column-based, which basically offers quite a bit of advantages over the CSV files we'll just talk about in a second. But let me show you how it works. Okay. So this is how a typical CSV file looks like, wherein what I'm basically doing is that I'm just reading some data set. I've created a Spark session, and then I'm just reading the CSV file. Whereas for a Parquet file, you have the same Spark session, and you're reading a Parquet file. I wanted to do a benchmark for this, but I'm not going to do it in the interest of time. I'm just going to run it once and see how it performs. Ta-da! It took like 3.4 seconds. Now let's see how the other dude performs. Sorry. It took 2.3 seconds. It was actually done on a very small data set. When I actually did it for the purpose of the slides, I ran it on a different machine on a larger data set, and I saw the speed wins from 5 seconds to 1 second. Now let's understand why that happened. There are lots of pros to Parquet files, and as I mentioned, it's basically because of it being a column-based setup. It has faster query in the sense that because it is a column-based setup, the queries can actually just use the subset of the entire file structure. So you're not processing the entire data file, you're just processing parts of it. Then comes better compression. Columnar storage actually allows for more efficient compression, which can significantly reduce the size. When I was testing on one of these data sets, I saw that the size was almost half of what you'd expect from a CSV file. Then comes schema evolution. Let's say you want to add a new feature to your data, or you want to add a new column, essentially. Parquet files, it's very easy to support that, as you don't have to read the entire data again and add it after every column. You just add it towards the end or wherever you want to. And finally comes improved data skipping. If you want to skip some columns or something like that, you can just skip the entire data blocks and add your filter criteria based on that. Okay, so next we have training a model. This is one of the most crucial and most time-consuming as well in an ML pipeline. A lot of scientific libraries do wonders when it comes to training and making an efficient code. Let's dive into one. Euclidean distance. So I don't know how many people do ML coding, but Euclidean distance is one of the most core concepts that people use to analyze similarities of some sort. It could be k nearest neighbors that you want to see, like is this one point similar to the other points in the neighborhood. Or it could be the clustering. If you want to cluster different points, you need the distance. It could also be the distance from the loss function or the error rate of an ML model. It could also be used for anomaly detection, like how far is this anomaly from the general trend. So over here, I have this very simple code snippet wherein you're basically finding the Euclidean distance. This is just the formula of the Euclidean distance, and you're using simple, non-vectorized way to do it. However, NumPy has a powerful concept called NumPy vectorization. It basically allows for high performance in a multi-dimensional array. It is a process wherein you can apply one operation to all the rows, to the entire array essentially, rather than iterating loop by loop on one element at a time. This can significantly improve the performance and as well as readability. Let me go through a simple example over here. Over here, we're just adding the number 10 to all the elements in the array. So in the first thing, it's basically like a simple for loop that you're using, whereas in the other one, you're using the vectorized operation provided by NumPy, which is basically like a single line. You just add it, and it automatically applies it to all the elements. And this significantly improves the time. I have the time over here, which for the first one was 0.02 seconds, whereas for the other one, it was, I don't know, 0.6 milliseconds. But let's see how it performs. Okay. So I have this code wherein I'm basically finding the Euclidean distance in a non-vectorized way, which is basically just finding the distance between the 2 points each by element by element. And I have this other one, which is the vectorized way of doing it, which is significantly smaller code. It is just one line because it's already available by NumPy. And in terms of running it, it's pretty fast. Let's see. The non-vectorized one took 0.2 seconds, whereas the vectorized one took 0.003 seconds. Significant wins. I ran it on a larger data set on a different machine, and I saw that the improvement was from 400 milliseconds to 5 milliseconds. It's like 100x. But why is it better? There's several pros to vectorization. First is the speed. As I just said, that it's not loop-based. It's done for the entire array. It is basically because it's done at the C layer and not at the Python layer. We know for a fact that Python is slower than C, and NumPy uses all the computations in C, and so that's way faster. It's also better for the readability. We did see that the type of code that you're writing is much simpler and easier to read. All the calculations are abstracted. You don't have these low-level abstract calculations that you see in Python. It's all happening underneath. And then finally, scalability. As the input size increases of the input array, the vectorized approach is far more superior than the traditional loop-based approaches. This is essentially useful when you're working in industry and you deal with like big, large data sets. And finally, the last part that I want to talk about was data analytics. Data analytics and visualization is also core to the ML lifecycle. It essentially deals with understanding the data. You visualize the data to understand the distributions, the relationship, or the patterns that it may have. You also try to identify the insights in the form of the trends that the data has or is showing, which might be useful for your model development. And finally, to communicate results. It's far more easier to view what people are doing or what the data is trying to demonstrate than actually look at the results. It provides better visualizations. So yeah, Mostly for data analysis, what we do is that we try to find the mean or the standard deviation. These are like the very popular tools that people use, especially the data analysts, to identify like how the model is performing or what's the accuracy like, things like that. So yeah, this is a very typical example. It's just running the formula of the mean and the standard deviation and trying to find the time. And the better way to do is to use Pandas data frame. For people who don't know what's the Pandas data frame, it's basically two-dimensional labeled data structures with columns of potentially different types. I did not know it was a two-dimensional. I got to know that when I was writing this talk. They are designed for data manipulation and analysis. The argument over here is also very similar to the CSV versus Parquet that we just discussed, but we'll come back to that later. Let me show you how that looks like. So this is a very typical way of doing the mean, which is basically sum divided by the length, and the standard deviation. This is just the formula. But a better way to do this is what Panda provides. They already have these functions available for you. And in terms of speed, the typical one took 0.5 seconds, whereas, let's see what this one takes. It took 0.019 seconds. Pretty fast, I would say. I did this analysis on another data set, another machine again, and we saw the wins to be from 400 milliseconds to like 6 milliseconds. But why is it fast? I did mention that it is something to do with what we had for CSV versus Parquet files, and it is true. It is column-based, so it is faster. All these aggregation data processing operations are much faster in column-based. It is also two-dimensional. Another pro for Pandas data frame, which is not really related to performance, but I really like to tell people, is that it's heterogeneous in the sense that these columns can be of different types. They don't have to be, they're not very cohesive, that they have to be, let's say, ints or floats. They can be strings, or they can be whatever you want to have. And finally, they have label-based access. This, I feel, is a very powerful tool in the sense that you have all these columns marked by column names, which makes it very easy to read and maintain code. It's very convenient when you're developing these large applications and you're confused with like, oh, what does this column represent? What does this 10th column represent? Things like that. And finally, it also supports the vectorized operations. And all of these things are optimized at the C level of the Python data, of the Pandas data set. So you really don't see any of these calculations happen at Python level, which really speeds up the performance. When I actually saw this slide today, I realized that the bear that I have over here is neither Pandas nor polar bear, but let's deal with it. Please imagine like a pandas or a polar bear over there. Anyway, this is basically a very big debate on like, is pandas better, is polars better? I've had these massive debates and conversations where there is no right or wrong answer, but I'm just going to put in like what's the benefits of each of them. First, Pandas uses Python and has C extensions in the sense that all the optimizations happen at C level, whereas Polar, it's mostly written in Rust. Polar is also newer than Pandas. The performance of Pandas is slower, not just because of Python plus C, but also because it's mostly single-threaded, whereas Polar's, it is in Rust and it has built-in multi-threading in place, so it is much faster. In terms of execution as well, Pandas is mostly eager, whereas Polars is mostly lazy, so it adds up to the performance of Polars when you're actually having this applications builder. And finally, the ecosystem. I think here Pandas is a big winner in the sense that it has a very mature, large community. You get a lot of help and support. Whereas in Polars, it's very new, it has slower adoption, and you might not get a lot of support. But I don't know if that's too much valuable these days, given that we have vibe coding and ChatGPT coding. So we don't know. But this is my opinion. I feel like Pandas is good enough for most cases and is widely adopted in the industry. It's more mature, the APIs are more stable, and I personally prefer Pandas. Whereas I do have opinions about Polars. I think it is very creative. It has these fancy things like chaining and other mechanisms which really make Polars powerful. It can actually be, those potentials are more reflected in very large data sets. However, I do have inhibition to using it because it does have a huge learning curve. Okay, so conclusion. For anyone who's involved in AI in any capacity, you're supporting AI or something, you're working on the AI, or I don't know, who's not working in AI these days? All of you love Python scientific libraries. At the same time, everyone hates compute times. I just have one suggestion, that use appropriate data structure wherever you're trying to use. And happy coding. That's all. Thank you.